Good morning, everybody. So, anybody there? Oh, Corey's there, Fox is there, Patricia, Brandon, Corey. Thank you. Krish is there. All right, all right. Well, yeah, this is the last session before your spring break. So, thank you for participating in the class, anyways. Um, as I talked about it last time, based on the schedule, today, uh, I am supposed to only talk about 16.1, but I already have done that, all right? Since the next Thursday, I mean, Thursday after your spring break, you have a test, and that test is going to cover section 16.1, 2, and 3. Today, I will basically talk about these three sections, although I have already talked about 16.1, which is the Laurent series. And I have covered pretty much a part of 16.2, but yeah, there is an advantage of doing that because during the spring break, uh, you can review those sections, and those sections 16.1, 16.2, and 16.3 will be in your test, all right? So there is an advantage that uh, I talk about those. Okay. Any comment, any question? Well, so here is the uh, brief review of Taylor series. Okay. In Taylor series, the function is analytic at this point. So that means derivative exists in a disk centered at this point. If that is the case, then not only derivative exists, but n's derivative also exists for any n. And we can have a Taylor series of the functions centered at that point. Now, since the function is analytic at this point, the series converges very nicely. And all we have here is a constant and positive, all right, positive exponent, positive powers of z minus alpha. Of course, the question is, what about this constant an? Oh, that constant an is here, right here, the nth derivative evaluated at alpha divided by n factorial, that can also be expressed in terms of integration. Now, I am reviewing this because next, when we talk about Laurent series, the Laurent series basically follows the same pattern. The only thing is the function is not analytic at alpha. The function doesn't have derivative at that point. In fact, alpha is a bad point. And as a result, we are going to have negative exponent or negative powers of z minus alpha. We are going to have z minus alpha in the expansion in the denominator as well. All right, that's the difference. Good. Well, when alpha is a bad point, remember, if the function has derivative in the neighborhood of alpha and alpha itself, we have no problem there. Alpha is a very beautiful point for the. But if alpha is a bad point, we classified alpha. Sometimes it is what we call isolated singularity. Okay. We have two. For bad points, in general, we have two categories. One is called isolated singularity. The other one, non-isolated singularity. Well, isolated singularity, just the term, the name is very descriptive. It basically says, okay, the function doesn't have derivative at alpha, but it does have derivative at other points of a disk. Like this one here is an example. See, the two bad points are 3i, negative 3i. These are isolated singularities, okay? These are at every other point. I mean, if you exclude these 2 points, then the function is a beautiful function. So these type of points we call isolated singularities. Do we have non-isolated singularity? Yes, we do. And usually it happens when you're dealing with logarithm, okay? Here is the logarithm. Choose any point on the negative direction of x-axis or even 0. Although log of negative 3 is defined, but the function doesn't have derivative in this area, okay? So we cannot isolate and say the function only doesn't have derivative at negative 3. No. No matter how small the disk you choose, still there are infinitely many points at which log of z doesn't have derivative, okay? Those are called non-isolated singularities. In this course, we are not going to deal with non-isolated singularities, only isolated singularities, all right? So, type A, isolated singularity, remember, derivative doesn't exist at alpha, but derivative exists in all other points of this disk, okay? So, symbolically, we say this. In this disk, every point in this disk is z minus alpha less than r. But we exclude alpha. Excluding alpha, you don't want z be the same as alpha, right? So be positive. And that is when we say derivative exists in here. That is the isolated singularities. Okay. Well, it's a good review. I'm just reviewing the material, make sure that we understand. Then I talked about Laurent series. So Laurent series is for those isolated singularities. So the function is analytic here, except, you see, derivative doesn't exist at this point, but it's fine every other point. If that is the case, we can write a power series expansion in center being Z naught. But in this expansion, we are also going to have Z minus Z naught in denominators, all right? And that is when we have negative exponents of Z minus Z naught. How about AN? The AN follows the same formula that we had in Taylor series. Okay, here is AN. Well, we did, I gave you a bunch of examples as how to find the Laurent series. And remember, the Laurent series, if we find it is unique, so we always would like to try the shortcuts, okay? Now, something is very important here. In this expansion, when n is -1, here this will vanish because this will be to the 0 and it's 1. So it will be just a to the index -1 is 1/2 pi I integral of f of s ds. And always that is what we are after. We want to find integral of f of s ds over a closed curve. Okay, that observation is extremely important. So this number, which appears in that Laurent series, is called residue of the function at that singularity. Residue at that singularity. Oh, we need this number. Why? Because integral of f of z dz, when the singularity is inside this closed curve, is 2 pi I a index -1. And how do we find this index -1? That is in the Laurent series. When you write Laurent series, this is it. The number that is multiplied by 1 over z minus z0. So this number is extremely important. And that is one of the reasons we like Laurent series, all right? That's one of the reasons we like Laurent series, because we need this number. We need this coefficient. Well, I also talked about this, some sort of naming from constant and to the right, all the powers, positive powers of z minus z0. This is called analytic part. The part that contains all the terms where z minus z0 is in denominator, this part is called principal part. Principal part. We are going to classify these singularities, isolated singularities, based on this principal part. Okay? So, There are three types of singularities. So you look at here, the principal part, okay, the terms where the exponent of z minus z0 is negative. We really don't have any problem here. This analytic part, we like it. We don't have any problem here. So we concentrate on this part, the principal part. And we classify these isolated singularities based on the structure of this principal part. Okay. We have three types of isolated singularities. One of them is called removable. And removable happens when you write the Laurent series, and in the Laurent series expansion, you don't have any term here. So we don't have any principal part. Oh, as an example, here we go. Sine z over z. This is sine z, expansion of sine z, and you multiply by 1 over z, you get this one. See? We don't have any z in denominator. So z equals 0 is removable singularity for this function, although it looks really bad. Because in mathematics, as you know, we don't divide by 0, and we don't like zeros in denominator, and those are singularities. But for this particular one, after we do the Laurent series, we don't have the principal part. That is called removable singularities. Okay? Sorry about this. Thank you, Corey, for reminding me. Okay. So I was trying to say in the Laurent expansion, in part 1, when it was removable, you didn't have any negative power of z minus z naught. But if there are finite number here in the principal part, when it is finite number, let's say the highest degree in denominator is n, provided this coefficient be non-zero. if this happens, we only have, let's say, n of them in the principal part. This Z naught, we call it a pole of order n. Okay? Oh, this got to be non-zero. And remember this one. Oh, we like this one. This coefficient here. Oh, we love it. That is the residue. And I will talk about residue theorem today, and you will see how important this number here is. So this is pole of number order n. If we have a pole of order n, we can factor this largest power denominator, and then you will get this. And this part is a power series, right? And it's an analytic part, and is not zero at Z0 because we know that A negative 1 is not zero. So this gives us a very good understanding of pole of order n. A function has a pole of order n if and only if it looks like this. In the denominator, you have z minus 0, that singularity, isolate the singularity to the n. In numerator, you have an analytic function at z naught, and it is not 0 at z naught. All right, remember phi of z 0 or z naught, which is equal to a index negative 1, is not 0. Okay, so this is a good thing to know. Somehow, a characterization of pole of order n. An isolated singularity is a pole of order n if and only if you can have such a thing. Okay. So type 3, I talked about category 1, which is removable singularities. Here, pole of order n, then the principal part has finite number of terms. And now, the third category is when the principal part has infinitely many terms. So it is not just finite, it's infinitely many terms. And if that happens, we call that point essential singularity. Essential singularity, all right? So, type 3 of isolated singularity. And here is an example. So, let's look at this. Oh, we don't like 0 in denominator, right? So z equals 0 is a singularity here, is a bad point. But other than z equals 0, this is a beautiful function. That is what I meant by isolated singularity. Well, look, let's expand this. Of course, we will use shortcut. We know that the Taylor series, e to the w, this function is an entire function, has this expansion. So we use it right here. W in this case is 1 over z. And then multiply by z cubed. This is what we get. a constant. Here z squared, z cubed, right? This part we call analytic part. And the other part that in which we have negative powers of z, and that means z is in denominator. This part is called the principal part. And as you see, we have infinitely many terms. If this happens, we call that singularity, that isolated singularity, essential singularity. Okay, good. So one of the problems that you are going to get in your test, and of course in the homework problem, they will give you a singularity and they will ask you to, what type of singularity is this? Is it removable? Is it a pole? Or is it an essential singularity? And here I gave you examples last time. So we write cosine z. Z equals 0 is a bad point. It's isolated singularity. So we need expansion with center at the bad point. Then you multiply by 1 over z cubed. This is what you get. All right? This is what you get. This is the principal part when z is in denominator. So z equals 0 is a pole of order 3. Pole of order 3. Okay? Now, this number is what we love. Negative 1 over 2. The coefficient of 1 over z. That is what we call the residue. All right? So maybe I should mention it right here. So z equals 0 is a pole of order 3, fine. But always we want to know what is the residue at that particular pole, all right? So residue of this function, f of z, at z equals 0, okay, at 0, is the coefficient of 1 over z, which is negative 1 over 2. That is how one of the ways that we find residue of a function at its isolated singularities. Okay, so this was good because I am also going to talk about residues today. Okay, so next, I'm going to talk about zeros because zeros and poles, there is a very interesting relationship between poles and zeros of a function. Remember, poles are in denominator, back point in denominator, but zeros is something else. So what is definition of a zero of a function? Well, in calculus, let's say we have a function like this. You want to find zeros of this function. You do factorization and let it be 0. So 0 is a 0 of the function is those numbers that when you plug in, you get 0. Okay? If I plug in 0 here, we get 0. If I let x be 2, also I get 0. These are called zeros of this function. Well, the same thing in complex. We can have zeros in complex as well. But I'm going to give you a, very accurate definition of zeros if of course the function has derivative, especially in complex. So in here, because you have x to the 4, right? X equals 0 is a 0. We say its multiplicity is 4. Its multiplicity is 4. Okay? So now here comes in complex. We say 0, z naught is a 0 if, of course, plug it in and you get 0. Sure. But can we have a sort of multiplicity? Well, we can. How do we define that? Well, in this case, we call it order, 0 of order n. So instead of saying multiplicity, we say order n. So z naught is a 0 of order n if not only the function is 0 at that point, but its derivative is also 0. Its second derivative is 0, up to n minus 1 derivative also is 0. But the nth derivative is not 0. If such a thing happens, we say this is a 0 of order n. Okay? It's like the same as multiplicity. But when the function is analytic at that point, z naught, good things happens, because when you write the Taylor series of the function, okay, this is the Taylor series of the function, centered at this z. If these guys are 0, then the Taylor series looks like this. The Taylor series, because the first n terms will be 0. So it starts with this one. Okay? This is not 0. If this be 0, 2, then it will be a 0 of order n plus 1, but now 0 of order n. So this is non-zero. I can factor this because all of them have z minus z naught to the n. If I factor that, this is what I get. But here, this is an analytic function, a non-zero, okay? It is not 0 at z naught. So with this observation, if the function is analytic at that z naught, we have a very interesting characterization of a 0 of order n. It is a 0 of order n if the function can be written in this fashion. A factor of z minus z naught to the n times an analytic function that is not 0 at this point. Okay, so um, another type of problems that you will have in section 16.2 is they will give you a function that might be zero at some point, and they will ask you to find the zeros and to find the order of those the zeros. Okay, find zeros and order of zeros. But before going into that, you see now the correlation, the relationship between zeros of the function and poles of order n. All right, here is that correlation. So this function is analytic here, has a zero of order n. And having a zero of order n, remember, you can write it in this way. What happens to its reciprocal if you take reciprocal of this? This becomes in denominator. And this part is analytic. We don't have problem with that. But if you take reciprocal, that Z naught will be a pole of order n. Okay, so here is the correlation between zeros and poles. A function has a zero of order n if and only if its reciprocal has a pole of order n. That will help us to figure out either the order of a pole or order of a zero. Okay, here's an example. See, z squared times sine of z cubed. Sine of z cubed, I mean this. So it says find the order of zero of this function. Well, here is the sine of z cubed. We know it's a beautiful function. It's an entire function. So its expansion, here is sine of w. Replace w by z cubed. This is what you get. Now, you multiply by z squared. If you multiply by z squared, this is your function. Okay? And z equals 0 is a zero of order 5. It's a zero of order 5. Because if you factor z to the 5, you get this. This part is analytic, nice, beautiful function, and is not 0 at z0. If you plug 0, you get 1. So 0 of order 5. Well, so, right? That's it. So the expansion, the Taylor expansion, or any expansion will help us. And sometimes you have to do Laurent series expansion. That's fine. They will help us to find the order of zeros or order of poles, right? For this function, I could have 1 over z squared this. Then z equals 0 is a singular, isolated singularity. The question is, what type of isolated singularity is that? Right? Yeah, let me do it here for you. So I could have, let's call it h of z. One over z squared sine z cubed. Oh, look, z equals 0 is a singularity here, right? There are other singularities, of course, when sine of z is 0, sine of z cubed is 0, but at least we know that z equals 0 is an isolated singularity. The question is, okay, now that it is isolated singularity, is it removable? Is it a pole? And if it is a pole, what is its order? And, or maybe it is an essential singularity. We need to figure it out. But the correlation, the relationship between singularities or poles and zeros of a function is interesting. So in order to find the as a result is a pole, right? To find order of pole, you take reciprocal and find order of zeros, right? So this one has a pole of order 5 at z equals 0 because its reciprocal has 0 of order 5. Okay, all right, good. So now you know what is the relationship between zeros and poles. Anyways, here is another example. Oh yeah, my goodness, it's the same thing, right? So after this explanation, you know that y, z equals 0, is a pole of order 5 here, because denominator could be written like this. Okay, good. Any comment, any question? I don't see any questions, so I'll continue this. This another example. Oh, z equals 0 is a bad point, right? Isolate the singularity here. So the question is, what type? What type of singularity? Well, e to the z minus 1. Here is e to the z. E to the z is an entire function, beautiful function. You can have its power series expansion. This is actually Maclaurin series expansion, that's fine. So e to the z minus 1, you bring it 1 to this side. And then divide by z cubed. This is it. This is e to the z minus 1. You divide by z cubed. This is what you get. Here is the analytic part. We don't have any problem here. It's a constant, a number. This is all now positive exponent of z. Here is the principal part. So the largest degree in denominator is 2. So z equals 0 is a pole of order 2. Is a pole of order 2, okay? You just don't make judgment by looking at the function. Right here, it looks like we have z cubed in denominator. You might mistakenly say, oh yeah, it is a pole of order 3. But no, you gotta write the Laurent series. Laurent series expansion and look at the principal part. It's a pole of order 2. Do you remember this number 1/2? The coefficient of 1 over z? That is what we like, and we call it residue of this particular function at z equals 0 is 1/2. Okay, here's another example. Just make sure that we understand the topic. In this case, I want to look at this function. Z equals 0. Oh, definitely, it is a 0 of the function, because if you plug 0 for it, replace 0 by 0, you get 0. So the question is, what is the order of this 0? Well, here is again e to the I factor z, and e to the z minus 1 is right here. You multiply by z, this is what you get. So this part is analytic and is not 0 when you replace z by 0. So we can write it as z squared. So z equals 0 is a 0 of order 2. Is a 0 of order 2. Okay? Any comment? Any question? No question? Good. The question, of course, right now you could ask, is this the only zeros that we have here for this function? The answer is no. The answer is no, because this function, f of z, that I'm writing exactly the way it was given z e to the z minus c. If you factor z, sure, you get e to the z minus 1. What are the zeros of this function? Either this got to be 0 or this parenthesis got to be 0. So zeros of this function are z equals 0 and then e to the z becomes 1. E to the z becomes 1, which means e to the z becomes e to the 2k pi I. All right. Oh my goodness. So we have infinitely many zeros. So two k pi I are all zeros of f of c. What about the order of these zeros? Oh, well. So here is the order of these zeros. Let me put it in a question format. It's not Jeopardy, but okay. What is the order of these zeros? I would say it's just order 1 because the function is 0 at that point, but its derivative is not. Okay. Well, look. Definitely f of e to the, let's just concentrate on this one. It will be 2k pi I, that's fine. It is z well, z is e to the 2k pi I, so, but e to the 2k pi I is 1, so it is 0. Remember the definition of 0 of order n. Let's consider derivative, f prime of 0. F prime of z in this case. I'll apply product rule. So it's e to the z okay, here is the function. I want derivative of this function. So it will be derivative of this times this, derivative of this times this, plus z e to the z, and then minus 1. What happens if I replace z by 2 pi I? So f prime of 2 pi I here, well, let's put it there. Why not? E to the 2 pi I plus 2 pi I e to the 2 pi I minus 1. But this is 1. It's 1 and this cancel. And e to the 2 pi I is 1, right? So the answer is e to the, oh, sorry, 2 pi, e to the 2 pi I is 1. So it's just 2 pi I. And it's not 0. So only the function is 0 at that point. Its derivative is not. So it is 0 of order 1. We call it a simple 0. So e to the 2k pi I is a 0 of order 1. Oh, known as simple order, right? It's the simple 0. Instead of saying order 1, we simply say simple zeros. A simple 0. Oh, that was a good one. All right. So remember, you just don't look at it. This factor can be 0, of course. All right. We have infinitely many points where this is 0. So we shouldn't ignore those zeros. Okay. Any comment? Any question? I am glad that I explained this part well also. No question? Good. Here comes a review of Cauchy theorem. Cauchy theorem says if you have a function, it's analytic. By the way, you need this, all right? You need this for the test as well. If the function is analytic here, and there is no hole, no bad point, and you integrate over this curve, closed curve, the integral is 0. Done. But if you have some bad points, let's say we have p bad points, we can isolate these. And when I was talking about Cauchy's theorem and one of its consequences, the integral over this outer boundary here, it's called C, is the same as integral over these small circles. Now, what is the difference? The difference is in this, when you are integrating here, you only have one bad point inside. So here the integral over these many bad points inside that closed curve will be the same as integral over these little circles, each one just enclosing one of the bad points. Oh, that was one of the consequences of Cauchy's theorem. Now, then the question is, what about this? We like to find this. Well, depending on the bad point, of course. Since there is one bad point here, it's called Z1. If we write the Laurent series here, the coefficient of 1 over Z minus Z1 is what we call residue, right? That coefficient, 2 pi I times that, will give us the value of that integral. So you write the Laurent series, and this A minus 1 we call it residue, which is coefficient of this guy. So if you multiply by 2 pi I, so the integral f of z dz will be just 2 pi I residue of the function at that point. And this is called residue theorem. And this is the topic of that section 16.3. Okay, so this plays a crucial role in the integration theory. So this is the coefficient of this guy. We call it residue of function at that point. And this integration over the closed curve centered at that singularity, isolated singularity, will be 2 pi I residue. So putting these two together, we get this beautiful theorem, which is called residue theorem. You have a function. You want to integrate over this curve, but there are these isolated singularities in sight. What is the value of integral? The value of integral is 2 pi I times find residue at each one and add them. Find residue at each one of these and add them. Okay, this is residue theorem. And let me see, I give you an example. See how, of course, the question is, how do we find residue? So that's the crucial fact now. There are maybe, several ways of finding that coefficient of this guy. One way, which works, so always works, it just write the Laurent series in powers of z minus z0, and the coefficient of this guy is that your residue. That's always a very sure, approach. Now, if you have a simple pole means pole of order 1, then the function looks like this. And we like to find this b. This is the residue. How do you find that? Well, you can multiply by z minus z0. If you multiply by z minus z0, you get this. And you take limit as z approaches z0, you will find this constant. So this is when you have a simple pole. In fact, when you have a simple pole, there are three approaches, of course. One, writing the Laurent series, fine. This is, I called it part A. Here is part B. You can do it in this fashion as well. So this works especially when we are dealing with a rational function. So this is 0 at z naught, but that is not. And since it is simple pole, the derivative of this guy is not 0 at that point. So since this is 0, doesn't matter. I just subtract 0. Then divide by z minus 0 if you multiply by z. Then this is what you get. As z approaches z naught, this denominator, limit of this denominator, gives you derivative of denominator. So the next approach for simple poles is this. Numerator divided by derivative of denominator evaluated as z naught. Okay? All right. So this is the sort of another approach of finding simple residue when you have a simple pole. What if we do not have a simple pole, but rather we have a sort of pole of order n? Well, if you have a pole of order n, here I'm talking about just pole of order 2. And if you understand what happens in pole of order 2, then we can generalize it. If it is a pole of order 2, you expand it in the Laurent series. Looks like this. Now you got to multiply by z minus z naught squared. If you have multiplied both sides by z minus z naught squared, here I get a constant. Here this will be multiplied by z minus z naught, and the rest. Okay? Now, our goal is finding B. We need this one, which is residue. We need the coefficient of 1 over z minus z naught. So how do we find this? Well, here, if I take the derivative with respect to z on the right-hand side, derivative is, this is a constant, derivative will be 0. Derivative here will be b. And the rest of them all have the factor of z minus z naught. So after taking derivative, if I replace z by z naught, all these terms will vanish. I will get b. Okay? So if it is a pole of order 2, this is what we do. We multiply by z minus z naught squared, take derivative. And after taking derivative, we take limit as z approaches z0, right? Well, you can do it for z equal 3, n equal 3 with the same thing, but that requires two derivatives. And for a pole of order n, it requires n minus 1 derivatives, all right? So here is what we do when we have a pole of order n. That formula is a little bit confusing, but please review for z equal 2 and do it for z equal 3 by yourself to get a feeling that why we need such a thing. I'll stop right here, and this pretty much covers section 16.3. And next time, which is Tuesday after your spring break, I also have another review of section 16.1, 2, 3, and more examples to make sure that you can apply especially this formula, how you can apply this formula and you understand the residue theorem, because residue theorem is extremely, extremely important for us, extremely important in complex analysis. It's the highlight of integration theory. Okay, any comment, any question? All right, before I lose my voice, thank you everybody for participating. Only 10 of you participated in this class today. And have a wonderful spring break. See you the Tuesday after spring break. Bye-bye, everybody. Thank you, Corey. Thank you, Brandon. Thank you, Krish, Jared, Fox. Thank you, everybody.